Okay, but why?
Hello there, and welcome to the fourth episode of Biscuits in Biophysics. Now, to my left, I have the image of a house. And on my right, I have the image of a mug. Now, your task is to match this image with either one of those. Think you can crack it? Well, of course, this might be a simple enough problem for you to solve, but if you can find a way to teach a computer to solve this problem, then you can help create fingerprint scanners, retinal scanners, facial, or even speech recognition software. They all work based on the computer's ability to correlate one type of data with another. So how do we solve this problem? Well, we need to find a way to help the computer compare the two images and identify if they're similar or not, depending on some sort of a score we can assign. But the computer doesn't see images the same way we do. It looks at each image as a grid full of numbers, sort of like this. So how do we help the computer compare the two grids? Well, I guess we could try adding the numbers on one grid with their corresponding numbers on the other grid. But that wouldn't get us anywhere, because look, 5 plus 5 gives us 10, and 6 and 4 give us 10 as well, so there's no telling whether it's similar or not. We could subtract the numbers, in which case, yeah, it would work. The similar numbers would give us 0, whereas, there's a problem again. Now, if you look at 6 and 4, they give you 2, but 7 and 9 give you -2. So if you add up your score for the entire grid, then you're going to get 0. But that means they're perfectly identical. But these grids aren't perfectly identical at all, are they? So there's a simple solution to this. You could just square your differences, and that way you'd only get positive values everywhere. And since they are positive and distinct, they give you the correct estimation of the type of difference in each grid square. So there you go, you solve the correlation problem. Oh, you could simplify it a little more. Because if you recall, the square of a difference term can be expanded to give you this. And since adding two numbers in the grids doesn't exactly help much, you can just take it off. So all you're left with is that little thing over there. Quite simple, isn't it? So essentially all you have to do is multiply the numbers on each grid square and you can get your score. Wow, so that is a cross-correlation problem. Now this can be used for a variety of handy things, not just the pattern recognition softwares that I told you, but in biophysics especially. Let's say you measure a particular type of signal that comes out of an experiment, and you want to know how it evolves with time. Just like you multiplied a number with another over here, you can even multiply a function with another function to get what you call a cross-correlation function. So if this is a curve, then of course it's going to correlate completely with itself. But if you capture that curve after a few seconds and then try to correlate it, of course, it's not going to be the same. The correlation is going to be much lower. And that will help you decide how much it has evolved with time. And in image processing, cross-correlation can also be used to shift and rotate images so you can align them perfectly. And image alignment, if you recall from my video 2 months ago, is extremely important when it comes to solving structures in cryo-electron microscopy. So that, ladies and gentlemen, was the concept of cross-correlation. Now, if you found that interesting, then your mind is about to be blown in our last episode tomorrow when I give you another concept that's completely different from this one, but it uses the exact same equation. Now that is a concept of convolution, and we will explore that in further detail in tomorrow's finale of Biscuits and Biophysics. I am running out of biscuits, so I probably have to replenish that. Until then, stay safe, stay curious, and stay tuned for the next video.